I'm also very happy to share my recent research on Holocene temperature simulations and my thoughts on this Holocene temperature conundrum problem. Um, yeah, so I would thank you to the contributor, my advisor, Jeremy Liu, and my collaborator, Noni Thompson and Thompson, and my two Chinese colleagues. They also help with the Holocene transient simulations with isotope-enabled simulation coupled climate models. Yeah, so let me start. So for the background, just show you some background on Holocene climate variability. Firstly, obviously the climate forcing. We all know that the dominant forcing during the Holocene is the orbital perimeter change, which is what we call the orbital precession. For example, in today, in summer, the Earth is far from the sun, and in winter, we are closest to the sun. So we have a seasonal cycle, right? But during the early Holocene, about 10,000 years ago, um, in the winter, actually, we are very far from the sun, but during the summer, we are very close to the sun. So this causes and seasonal cycle change in the insulation, therefore causes the seasonal cycle change in temperature. So this time series shows you the top of atmosphere insulation change during the whole Holocene period. So you can see the insulation, this red line shows the JJA. Okay, during JJA, insulation decreases from the early Holocene to the pre-industrial. But during DJF, in contrast, the insulation increase. Here we shows the mid latitude North Hemisphere insulation. Okay, it is this kind of pattern, and we also have another two important forcings. One is greenhouse gases. So this line shows the CO2 concentration. You can see overall it the concentration increases from early Holocene to the pre-industrial about 20 ppm. Another one is the ice sheet volume. So we know from the early Holocene to mid Holocene, the ice sheet keep decreasing, but at the mid Holocene, after mid Holocene, almost all the land ice sheet disappeared. So that does not change too much till the present, till the pre-industrial. So, what will be the temperature response to all these forcings? Okay, if we just take a look at the time series from the proxy reconstructions, we can see overall over the whole North Hemisphere, all the proxies showing this black line. The temperature firstly increase from the early Holocene to the mid Holocene reaches the maximum at the mid Holocene and then gradually decrease from mid Holocene to the pre-industrial. So this maximum we call the Holocene thermal maximum. This is the whole North Hemisphere average. But for other regions like South Hemisphere and tropical regions, they are shown in these lines, colorful lines. They do not show very clear thermal maximum as we see in the North Hemisphere. Okay, so from the proxy, we can see this kind of pattern. Firstly, temperature increase, then decrease, seems to very well correlated with the JJA insulation change over the North Hemisphere, right? Like this line. So, but how about the climate models? Again, this line in this paper, the blue line shows the time series from the proxies. first increase, then decrease. But from the models, we can see the model will simulate a gradually increased temperature without thermal maximum. Okay, so this mm, model proxy inconsistency causes a problem. We call this Holocene temperature conundrum. Why is a conundrum? Because it's really hard um, to explain why model and proxy have this discrepancy. Because uh, like we can look at the forcing again in the annual mean, the insulation actually do not change too much. It's only about 1 watts per meter square change during the whole Holocene. But the CO2 gradually increase. This still have zero point 0.5 watts per meter square forcing to the whole climate system. And ice sheet also decrease, will also produces comparable radiative forcings. So that's why climate models, um, the temperature of climate models tend to respond to the increase of CO2 and decrease of ice sheet instead of the change of insulation. This causes the gradually increased temperature simulated in models. Okay. Um, and there are also sources of uncertainties in both proxy data and climate models. So one major uncertainties in proxy data is the so-called seasonal bias. You can think of most of the proxies, for example, the tree rings and other some kinds of ocean sediments. They are more biased to the warm seasons, as their for example, the tree rings, their grew seasons is in summer, in warm season, right? So their signals will be naturally biased to these warm seasons. So uh, this so the temperatures are reconstructed from these proxies may only represents for the warm seasons instead of annual mean. Okay, so this is a problem. Um, in the After the conundrum proposed in 2014, there are more efforts to reconcile the model and data. In 2021, in Bova's work, they tried to remove the seasonal bias from the ocean sediments, and they do after the signal bias removed, they do see a gradually increase temperatures over the global oceans. But the thing is that they are mostly based on marine proxies. But most of the other proxies are over land, right? And most of these land proxies still show a mid-Holocene thermal maximum. Okay, the temperature is positive relative to the present day, but all other multi-model simulations, they all show decreased temperature in mid-Holocene, except for the polar region, Arctic region. So the model data inconsistency still exists in most of the land regions. So the Holocene temperature conundrum is still an unresolved problem. So there are also many studies propose the model deficiencies, and they're trying to um, improve the model by adding missing boundary conditions. For example, they consider the volcanic forcing because from the from the records, they show that in late Holocene, there are a lot of volcanic events. These volcanic events will produce a lot of aerosols and dust to the atmosphere, then block the solar insulations, then cool the atmosphere, right? So this is one boundary conditions missing in most climate models. Another one is the land cover change, because during the late Holocene, due to the human activity, the increase of human activity, there will change the land covers and will reduce the albedo. Reduce the albedo and increase the thermal absorb of the land. So that will also uh, uh, yeah will also change the temperature over land. The next Another one is the vegetation change because uh, during the late Holocene, the vegetation tend to decrease, uh, and that will also due to albedo effect or evaporation effect will also change the temperature. So all these studies are trying to reconcile the model. Why model cannot simulate the late Holocene cooling? Maybe they miss some boundary conditions. Another one is the model feedbacks. There are several studies also study the sea ice albedo effect. They think that sea ice albedo effect may increase during the late Holocene that will enhance this feedback, so will produces the cooling over the North Hemisphere mid-high latitudes. Okay, they are from the model perspective. People also trying a lot of efforts to prove the model simulations. But the thing is that we can see as before, because the proxy itself has bias, especially the seasonal bias. So it's really hard to find good proxies to constrain the model, right? We also know model is never perfect. So we should find a better way to find a better proxies to constrain the model simulations or to validate the model. So that's one object for me to continue with these studies. Um, so how do we use? The thing is that we have the Holocene transient simulations using the isotope-enabled climate models, which we call it iTrace models. So with these iTrace models, we have data O18, so-called data O18. So we can directly compare the data O18 with proxies with these records, right? So for temperature, we know that most data O18 records representing temperature is from ice core, especially the Greenland ice core, Arctic ice cores. But for tropical mountain ice cores, their explanations still have a lot of debate. So I put a marker here. Okay, we are not very sure if it's a temperature proxy. But overall, we can use Greenland and Antarctic ice core data weighting as a good way to constrain the model simulation on data weighting. Okay, so we can do the direct model data comparison through this approach. So this figure shows how the model performance in data weighting simulations. Here, the black line shows the data weighting ice core from the proxy, from the ice core itself. So this is the Greenland. We can see overall, the proxy is showing mid, the early or mid Holocene maximum in data weighting values. But after that, we'll show a decreasing trend from the mid Holocene to the pre-industrial over all these Greenland ice cores. Okay, and how about in the model? This is shown in blue line. So the simulated model data weighting in precipitation also showing increase during the early Holocene and reaches the maximum during the mid-Holocene and then decreasing trend from the mid-Holocene to pre-industrial. But the thing is that the decreasing trend from mid-Holocene to pre-industrial in the model is much more weaker than that shown in proxies, right? Very weak, especially in like Greenland and Diet 3, these sites. So so here we see that model indeed has some uncertainties or weakness, okay, especially the weak response over Greenland. Another one is the surprising is over the tropical region. You can see the tropical region show very similar decreasing trend to the Greenland, okay, in proxies, they show decreasing trend. But in our model, they show a little bit increasing trend. So this contrasting trend is very surprising, actually. If if data weighting in precipitation an indicator of temperature, we cannot explain this trend. So this is another topic, actually. I'm trying to explain why model data is inconsistent over the tropical region. But I think overall, it's the explanation of data weighting itself may not be temperature anymore in Holocene. But this is not the topic in today's talk, so I will just leave it here. But yeah, but here overall, so the conclusion here is that our model do have some uncertainties, especially simulating the cooling trend from the mid-Holocene to the pre-industrial. Their response is too weak. So why that happens? Where is the model uncertainties comes from? That's my another question, right? We should further investigate where the uncertainties of the model simulations coming from. But it's not a very easy way to just directly find the model uncertainties because we know in our present day we have a lot of different kinds of observations. We have observations of temperature, right? Observations of cloud covers, observations of sea ice. So directly we can directly like show the model performance, constrain the model performance. But for the Holocene period, we do not have direct observations for all these kind of climate variables. So it's really hard to investigate the uncertainties. So one way we thought is an indirect way is using the multi-model simulations. Okay, we know in CMIP 6, they have a paleoclimate model intercomparison called PMIP 4, right? They have about 14 models. Okay, so because each models they will simulate different temperature response. We know maybe there are some model may simulate very warm mid-Holocene temperature, but some model may simulate cold mid-Holocene temperature. So, um, uh, so by trying to investigate why model simulate different temperature response from this different model, multi-model difference, we may find the model uncertainties simulating the temperatures. Okay, this is a direct way. Um, so in addition to model, we have to find a reference too. So we have a new proxy reference called temp12K dataset from Kaufman. Okay, so this dataset, the advantage is that they incorporate different sources of proxies, and they also labeled they also explicit labeled whether the temperature is annual mean temperature or summer temperature or winter temperature. So that will give us a good reference for our model simulations. Okay, so let's first look at how the PMIP4 model simulate the mid-Holocene climate. So the difference, okay, the first thing is we have the PI or pre-industrial simulation, pre-industrial control, right? They are just everything is the same as the present day. But the difference in the mid-Holocene simulation is we change the orbital parameters, okay? And then we change the greenhouse gases um, concentrations like here. But in addition to these two forcings, all of other forcings like ice sheets, vegetations, aerosols, they all keep the same as the pre-industrial. Okay, that's the very important settings. Um, yeah, so this map shows you the concentration of the proxies in temp12K. We can see most of the proxies located in Western Europe and yeah, North America. But like in the Asian or other region, we do not have too much proxies. So basically, if we want to compare the model with this proxy references, we have to focus on the North Hemisphere mid-high latitudes. Okay. Um, okay. Now let's first look at the mid-Holocene temperature response over all different PMIP4 models. This shows the annual mean temperature difference between the mid-Holocene and pre-industrial. Um, Over all these 14 models, including iTrace, we have 15 models. Okay, you can see overall different models have very different response patterns, right? For example, in EC Earth model, you can see a very clear warming during the mid-Holocene in North Hemisphere compared to other models, right? This warming is very large, and the average warming averaged over the proxy sites, they give us zero point 0.7 degrees. Okay, compared to the proxies it's about zero point 0.5. So this only easy model simulates the comparable magnitude of temperature shown in the proxies, but other models showing a very relative weak North Hemisphere warmings. Okay, but especially, for example, in iTrees, our simulations, transient simulations, uh, during the over the North Hemisphere regions, the temperature response in mid-Holocene is the minus. It tells us the mid-Holocene is cooling. Okay, instead of easy model, they show warming. So based on that, we just categorize all these 15 models into three categories. The first six models, we categorize them as warmer models. Okay. And the last six one, we call them cold models. And the middle four one, we call them mediate models. Um, so uh, here is the thing. We can see the multi-model, the temperature response, they have a very large difference, right? Or large multi-model uncertainties. You can see the model uncertainties is about 0.38, but the model mean, okay, the model ensemble mean is only 0.16. So that means the model uncertainties exceeds the model ensemble signals. That is the thing we find in multimodal simulations. And compared to the temp12K, the temp12K, the ensemble signal, not ensemble, sorry, the signal is zero point 0.5, but the uncertainties is only zero point 0.1, right? So the model problem is that the multimodal uncertainty, they exceeds the ensemble signal. So which is very which tells us the model simulation itself is a very large problem. Okay. And we can also this into different seasons. Okay. For example, for JJA, we can still do the same thing. JJA, the reference temp12K dataset, they produces a very significant warming. Okay. In mid-Holocene, zero point 0.9 warming, but their uncertainties is only 0.16. Models we can see is encouraging because model also simulate comparable warming in JJA, right? About 0.87. Their uncertainty is also smaller than the signals. So that's great. That's tells us most of the climate models, they can simulate the boreal summer temperature very well because because we know the boreal summer, the insolation in the North Hemisphere just decrease. So model can just capture this force this response, just decrease in temperature response very well. But for other seasons, for example, the boreal winter and autumn seasons, you can see the model uncertainties exceeds the model ensemble signals. For example, in DGF, the model uncertainty is zero point 0.7, but signal ensemble signal is 0.6. And in SON, the boreal autumn model signals 0.2, but the uncertainty is twice of the signal. So that tells us the large annual mean model uncertainties is mainly come from the boreal winter and autumn season. Okay, so that gives us another very important information is that the very difficult thing for Holocene temperature simulation is coming from the boreal winter and autumn instead of boreal summer. Okay. Uh, um, here, so here we see because we see the very large model uncertainties, and maybe we see that in in a warmer model, temperature if it's warmer in mid-Holocene, they may be maybe the model is more sensitive to insolation forcings, but more models with cooling temperature in mid-Holocene may be insensitive to insolation forcings. But we this is the thing we get, but we still have to find a quantitative way to just to calculate the sensitivity of the model to insolation forcings. Okay. Um, so far, we have a lot of work working on the model sensitivity to greenhouse gases forcing, right? So we know a term called equilibrium climate sensitivity, which is the uh, global mean temperature response to double CO2 forcings, okay, on the basis of pre-industrial. This one, we have a lot of work, but there are so far we don't do a lot of, we don't work on the model sensitivities to insulation forcings. So one way to isolate the insulation forcing of temperature from the total temperature change is that because we know mid-Holocene, we only have two major forcings. One's from greenhouse gases, one is from insulation. So we can just directly using this decomposition, okay? Because we know the climate sensitivity, okay? So we can just estimate about 20 ppm lower of CO2 during the mid-Holocene will causes how much cooling of the temperature produced by greenhouse gases. And then the residual one will be the temperature response due to the insulation change. Okay, so this figure just directly showing us the warmer temperature or the warmer models, okay, will have higher sensitivity to insolations. Okay, they have a very significant positive correlations. Okay, but colder temperatures is due to the weaker model sensitive to insulation. Okay, this is just improve that the model sensitivity to insulation is very important to uh, the mid-Holocene temperature simulations. This one is more clear. Okay, from the map, we can show that the full response, which is the original model simulation on data on temperature response, we can see it's almost due to the insulation response. Okay, for example, the warm models warming North Hemisphere is due to the model sensitivity. It's because model is sensitive to the insulation forcing in warm models, but the cold models is because model is insensitive. So that is mostly due to the insensitive of model to insulation response. And the model if sensitivity of CO2 between the warm model and cold model do not have too much difference. Okay. So, and again, I will highlight here. You can see the dotted dots here tell us the model is almost consistent. Okay, they are consistent over the tropical regions, but the most inconsistency is coming from the North Hemisphere. Again, the mid-high latitude North Hemisphere. Okay, so we can naturally think of this. That may be related to the Arctic polar amplifications, right? Why model is so much different from the warm model and cold model in this region? Maybe it's due to Arctic polar amplifications. Okay, But we have to further investigate this. Uh, why this model, this uncertainties, where is that coming from? Multi-model uncertainties. So we think of a good way to track these uncertainties. We know that we have heat budget equations on near the surface. It's like this one. So we can decompose the temperature, surface temperature change into several parts. The first part is the solar insolation change. Another part's called the surface albedo change, right? Another one is the downward long-wave radiation change. And another one, latent and sensible heat. And the remaining one, heat storage. All these process will contribute to the changes of surface temperature. So by examining all different climate models, all these terms, all the climate models, we can diagnose all these terms, and we can diagnose their contributions to the surface temperature change. So we can we can have a way to find where the multimodal uncertainty is coming from. Okay. Um, Further, we can decompose the long-wave radiation into the cloud reduced long-wave radiation and clear sky long-wave radiations. Okay. Uh, yeah, so I have about 15 minutes. Okay. Um, yeah, so we can here, this is the results of the decomposition. Okay, again, we first look at the total response. So this map showing the annual mean difference between the mid-Holocene and PI, and also the difference between the warm and cold model ensemble. Okay, again, we see the warm and cold model difference, large discrepancy, mainly from the mid-high North Hemisphere region. Okay, so how which process contributed to this difference? We can see the most dominant contribution coming from clear sky downward long wave radiation. Okay, and we should point out that this clear sky it is so abstract. So how does that coming from? Why is that the dominant one? That because the clear sky downward long wave radiation is they are proportional to two physical process. One is the column temperature. Okay, because if the column temperature is higher, that will produces larger downwave backward long wave radiation to the surface. Okay, and another one is the moisture content. If the moisture of the air is, we have more moisture within the air, then the downward long wave radiation will also increase. So that's the two thing causes the change of clear sky downward radiations. Okay, and another thing, in the Arctic region, the albedo effect is also important. So albedo, we will naturally think about because it's mostly over this Arctic Ocean, right? We will naturally think that will be uh, due to the changes of sea ice. Okay, sea ice albedo feedback. Another one is the cloud sky long wave radiation change. That tells us because if the um, clouds decrease, then the cloud will also, if the cloud increase, the downward long wave radiation will also increase, then that will warm the surface temperature. Okay, another one is the stored heat. The stored heat may also relate it to the sea ice, and I will also explain this further later. Okay, so this is for annual mean, but for JJA, we can see the albedo. The annual mean albedo is mostly coming from the JJA, which confirm our thoughts it's coming from sea ice because in mid-Holocene, the insulation increase, right? So the sea ice itself will decrease. The decreasing sea ice due to the due to the decreasing albedo will further warm the surface. That's why will causes this very strong temperature increase in warm models. And the clear sky downward non-wave radiation is also very clear in JJA. That is mostly related to the air column, the whole air column warming, okay, what produces this the surface warming. And for DJF, um, the the very dominant one is coming from the stored heat. Okay, this is not very intuitive because we know that the heat, this tells us the heat is coming from the ocean. Okay, the ocean heat will warm the atmosphere. But why? How that warm the atmosphere? The thing is that in warm models, the sea ice decrease a lot, so that will increase the surface temperature, surface sea temperature. So that sea surface temperature increase, that signal will just extend it to the to later in DJF season. Okay, so this kind of warm signal will stored in the ocean and release later to the atmosphere in DJF. That's why still we think it's the sea ice effect. Okay, through the air sea inter through the ocean storage. Another one is still coming from the clouds because in DJF, in warm models, the clouds they simulate more clouds will produces more backward downward radiation that's warm the surface. The clear sky downward radiation, I did further diagnosis, is mostly coming from the moisture latent heat. Okay, the warm models is much moist than the dry models. Okay. So there are too many details here, but the overall, we can have a summary here is that compared to the warm models and cold models, why warm models is simulate warmer temperatures is because warm models simulate less Arctic sea ice. And due to sea ice albedo feedback, they will produces warmer temperatures over the Arctic regions. And also warm models simulate more clouds over the uh, mid low latitudes in the North Hemisphere. Okay, that produces more downward long wave radiations, thus warm the surface. Okay, this is two main process in the summer. Okay, so for the winter, the two main process again is the release of stored ocean heat to the subpolar atmosphere, and this heat is actually coming from the previous summer because of the sea ice loss. Another one is also coming from the clouds and moisture. Okay, so I think the new thing here compared to the previous studies is that we think the model inconsistency or the model uncertainties, multi-model uncertainties, is not just coming from the sea ice albedo effect. So it may also coming from the model clouds and radiation feedback. Okay, this is the new thing we should highlight here because we know that even in recent or in present day climate, the model uncertainties in simulating clouds they have a lot of uncertainties. Okay, so these uncertainties inherently will also exist in our paleoclimate simulations. Okay, and here I should again highlight one thing. In PMIP4 simulations, we do not have land cover change. We do not consider vegetation change. We also do not consider the albedo change. So all of these model uncertainties is coming from the climate system itself, internal feedbacks. Okay, we can call this either Arctic sea ice or cloud radiation feedback. All these feedbacks is called internal feedbacks because they are not a direct response to the forcings, right? Even if we do not include all these other different kinds of forcings, we still simulate very warm, like North Hemisphere in some models, but relative cold North Hemispheres in most of other models. So that's the thing, is that we should highlight maybe just the internal feedbacks itself is very important. It's important enough than the other external forcings. Okay, that's the thing I want to highlight from our results. Um, so just have some uh, conclusion here. The first conclusion is that the intermodal uncertainties in PMIP4 in mid-Holocene temperature response, especially the annual mean temperature and the boreal autumn and winter temperature, their uncertainty exceeds the ensemble model signals. And their large uncertainties, especially located over the mid-high latitudes in the North Hemisphere related to the polar amplification. Okay. And the second thing is that the boreal winter seasons are crucial for constraining or reducing the model uncertainties in annual mean temperature. So I think this is another new conclusion, is that we have to, even if we want to improve the model insulation simulation in the future, we have to focus more on boreal winter seasons, and also autumn seasons. Okay. For the summer season, we just show it model is already did very good job. The third conclusion is that the relative cold model temperature in the mid-Holocene in most climate models maybe arises from the low model sensitivity to insulation forcing. Okay, and the most important thing for the future climate simulation is that we see there are large model temperature uncertainties in North Hemisphere, and these large uncertainties is coming from the internal model feedbacks. For example, sea ice albedo, cloud radiation, and external forces, other external forces, which is not included in the PMIP4 models, maybe not that important. Okay, that tells us maybe we do not have to produce so much effort uh, uh, on improving the external forces with Holocene temperature simulations. Okay, this is the reference paper of the talk. And another thing, just have maybe I have to use one minute, is that I would recommend a new research from my advisor, the seasonal temperature conundrum for the Holocene. So from this new uh, studies, um, just focus on the seasonal amplitude between the DJF and JJA. Okay, it's showing that the model do have a very large seasonal amplitude during the mid and early Holocene, but the proxies just showing very low amplitude of seasonal cycle. And further, this paper gives us very strong evidence showing that maybe the proxies have a very large uncertainties or have a very large bias in this seasonal amplitude, and also highlight that we should focus on the winter proxy reconstruction instead of summer. Okay, and models of winter reconstructions have very large uncertainties, especially the the how to say pollen. Yeah, the pollen proxies have large uncertainties for the winter reconstruction. And if you are interested, I would really recommend you to read this paper. Okay, that's all for my today's presentation. Yeah.
Okay.